Okay, an example of a conservation of momentum problem. And the situation here is that we've got a vehicle of some sort that is at rest when it explodes. Oh no. And the situation that we've got is outlined here. We've got two masses, here and here, that have velocities of 30 meters per second in magnitude, but at right angles to one another. And then we've got a third piece that we're given is 3 times the mass of the other ones. We're not told what the masses are, but we know that this one's 3 times as massive. And we want to know what is its velocity, magnitude, and direction. Now I've sketched in like a little guess about where its velocity might have to go, but we're going to find out what it exactly has to be. All right. So we know in this situation that all of the forces that caused that explosion are internal to this vehicle. And so that means that we don't have to worry about those forces changing the momentum of the system that consists now of 3 pieces. So momentum is conserved. And that means that since we have 2 dimensions here, we may as well split, kind of like we often do with the sums of forces problems, into P0x is equal to P final x, and momentum initial in the y direction is equal to momentum final in the y direction. And initially it is at rest, so that means that the left-hand side of these 2 things just goes to 0. And the right-hand side, well, if we use the usual thing where this is x, or rather this is y, and this is x in terms of our axes, well then there are 2 things that have x components potentially. One that we know about, which is this guy. So we put that term in first, say, and that'll be mv. And then we know that the other one is going to be some velocity. We don't know what it is, and that's that. So in the y component, much the same situation, except now we've got that little piece associated with this one right here. And then we have this other piece whose direction is undetermined, though if you think about it, we probably know what that is. Oh, this is an x component. There we go. And then y component. And if we solve for each one of those things, then what we get is negative mv over 3m. The m's cancel. And so we know that our x component to the velocity here is just going to be 10 meters per second, negative 10 meters per second along the x-axis. And following a very similar set of circumstances over here, we get that the y component to this velocity is also negative 10 meters per second. And if we sketch that out, we get this and this. And so v, the thing that we're looking for, or v3, I guess I've called it here for the third piece, is just going to give us square root of 10 squared plus 10 squared. That is 14.1 meters per second, rounded to 3 sig figs. And that's its magnitude. And the angle, well, if we just go for this angle right here, internal to that triangle, then we've got, well, we don't actually need to do this out, do we? We can do that one in our heads. That's 45 degrees. If we measure from the positive x-axis, as we usually do, then we get an angle of 135 degrees. So our answer is that this thing should have a velocity of 14.1 meters per second in a direction of 135 degrees relative to the positive x-axis. Okay, nice simple 2D conservation of momentum problem. Enjoy.